right? And 2, we're going to go like this. We're going to go, this is going to be 0, still theta, but in this case we want y, or g of theta, whatever we want to call it. Again, here's 1, -1. Nowhere near low enough. Okay, and again, here's 2 pi. Here's pi. Pi over 2. 3 pi over 2. Pi over 4. 3 pi over 4. 5 pi over 4. 7 pi over 4. And again, with these, now I want to graph 0, 0. And again, 2 pi 0. Now we've also got pi 0. And then we've got pi over 2, 1. And 3 pi over 2, -1. Followed by pi over 4 and 3 pi over 4 have our 0.707 values. So this is up here. This is up here. And 5 pi over 4 and 7 pi over 4 have our negative 0.707 values. Here and here. Which again, okay, so we get something that looks like this. Now, these are what are called periodic. Because if we then continued this pattern, and wait, what do you mean continue? Yes, if we went beyond 2 pi, because of course we can, right? 2 pi plus another pi over 6 would get us to, that's 12, so 13. 13 pi over 6 would get us back to root 3 over 2 again on the horizontal value, and 13 pi over 6 would get us to positive 1/2 on the vertical value. And then we could just keep doing this over and over and over again. To say like, okay, this is going to be 8, 9 pi over 4. Would get us a root 2 over 2 by root 2 over 2. Any number of rotations that we want to go, that's going to then add more to this, and we're going to end up with all these same values all over again. And this is the nature of a periodic function. Regardless of, what kind of function it is, what we're going to do is we're going to go some amount of distance horizontally, and we're going to end up back at the same function values over and over and over again in the y direction that we had in the first period. So this is going to be our primary period, essentially, from 0 to 2 pi. And say, like, in this first rotation, here are the values that we get for this. Makes it really exciting to work with, because it's like, well, if it's periodic, then I can just repeat this. Yeah. This is kind of the way that your car's engine will work. So it will go up and down in this particular pattern thousands of times per minute, RPM, right? Rotations per minute. And if you increase or decrease the speed, then obviously it changes exactly how long the period is. But if you maintain the same period for any amount of time, you don't change the gas. Yep. If you don't change how you're pressing the gas, it'll still continue at the same RPM, and it'll have the same frequency. It'll have the same period length. Now here's the other thing about this, is that all functions, not just these, not just periodic functions, not just anything else, all functions can also be used, or we can use y equals a times f of b times quantity x minus c plus d to do function transformations. These are the basic ones. So we have a linear function on the inside and a linear function on the outside. So the linear function on the inside is dealing with our x's, so b times the quantity x minus c. And our linear function on the outside is dealing with the function itself, so a times f plus d. And the way that you make it work is you say, okay, well, what does a do, right? It's a multiplication on the outside of the function. So if we're taking a function value that's coming out of the function, that's our y values for the function. So then if we multiply those y values by something, we're going to take the distance that it is away from, in our original functions, 0, right? If you multiply 0 by anything, it stays at 0. If you multiply it by 2, if you multiply any of those function values by 2, then their distance to 0 is going to double. So here, this is a multiplicative scale factor. And it's specifically vertical. So I will often call this a vertical stretch factor. So in this particular function, we see that it's going to take all these values here, and it would, if it's like 2, for instance, then basically all that's going to happen is our value here, which is the top, is going to get multiplied by 2. And all of the intermediate values are also going to double in size. So this thing at root 2 over 2 just becomes the square root of 2, because you just doubled it, right? It'll be 1.4. And then this one up here is going to be at 2. This one's still going to be at 0. This one's going to be at -2, negative root 2. So our vertical stretch factor is also known in terms of trigonometric functions specifically. This is also what's known as the amplitude. So you probably heard of amplitude modulation, which is one of the options that your stereo, your radio has. It is receiving signals from in the radio spectrum, which have a particular frequency. And then what it does is it reads, okay, of all the stuff that's coming in on that particular frequency, it's going to change its vertical. Hey Edzu, good evening and welcome. My name is Obi-Wan Pez. This is N Simplex Pachinko. We're currently discussing what is this? Function transformation, and specifically how it relates to trigonometric functions. If you have any questions, let me know. Okay, so our multiplicative scale factor is going to talk about the amplitude of these waves. And so your amplitude modulation radio is looking at all the stuff coming in a particular frequency and saying, how is it changing its amplitude? You could set it for like a particular level, whatever it is. And when you turn the knob on the radio, it picks up the stuff that's at a particular amplitude, and then it looks at the I might be wrong about it. It might be that it looks at the stuff, it looks at its frequency, and like that tells it how to spit out the signal in terms of what it sounds like. I don't remember exactly how it works, but that's what your amplitude modulation is doing. Your frequency modulation, your FM radio, is looking at stuff that's coming in at a particular frequency, and then the amplitude is telling it how loud to be for all of its particular sounds. So it's all really cool stuff, and I don't really know enough about it to really get it, but working on it. So oftentimes we do have a Discord server that is here. This is Penn Center's Discord server, but we all kind of use it. If you go to the either Maths forum or Maths chat, I am currently there, so, or at least I have it open. I can take a look and check things out. Yes, waves are a little important. So it's not until you get into like differential equations, which is beyond Calc 2, that things become like absolutely super important in terms of like, how do you build an electrical circuit? This is all 100% dependent upon this trigonometry and calculus that we've built over, millennia at this point. One of the other really big things was that we, yeah, and like computer engineering would require more, specifically talking about like RCL circuits and things like that. Computer science, in terms of yours, is much more, I would suggest, probably algebraic based. And so like you want to understand mathematics to calculus, etc. level, but that's going to be slightly different. So you're not going to need it necessarily in terms of really. You're not always going to need it in terms of like, in terms of the very specific things that you're doing. But stuff like neural networks, AI systems, etc., need a lot of differential equations in order to understand how like all of the individual pieces work. Okay. And I've also done, my spouse and I did a lot of work. I shouldn't say a lot. Took a class for our master's level in neural networks. And so that was really cool to try and understand all of the little nuances that existed between like trying to build AI systems and differential equations and trying to figure so many things out. Definitely needed Calc 2. Differential equations was, you know, I mean, it was necessary for both of our degrees, but it helped understand like how to make this stuff work. Helped us understand that. Okay, our D here, and not quite there, is actually taking those y values that are coming out of the function and then adding to them. So here, if we took this 0 value and we just said +1 at the end of it, then that would take that 0 and move it up to 1. If we took at pi over 2, we get a value of 1 back, +1, it adds 1 to it, makes it 2. Okay, and then this 0 moves up to 1, this -1 moves up to 0. So everything is equally moving up one space. So this is going to be a vertical shift. And you notice that around y equals 0, what we really see for these functions is that this is essentially a line of symmetry, not 100% like it reflects over, but the stuff that we see above and below are equally balanced. So this becomes what I call the midline of the function. Right, so y equals d. So this is going to be called the midline of the function. That's what I call it anyway. Okay, and then when we take the stuff from the inside, our b some of this stuff gets a little bit harder to see, like what exactly is going on. We may have to do an example, but if you were to multiply the inside of the function by 2, right, what you're doing is you're taking the x value and you're making it twice as large as it should be before finding that value of the function. So you're saying like, okay, I'm going to treat this point as if it were twice as big. And that value over here is going to get dragged back to where we are currently. And over here it does the same. So let's say from 0, right? If you multiply 0 by 2, it's not going anywhere. So that doesn't change anything at the center. But anything that is negative, we double its distance, look at its y value, and then pull it back over here. Any positive x values, right? We find its x value, find the distance. Nope. We find the x value, double its distance, take that y value, and bring it back here. So in either case, it's taking the stuff that's out here and essentially having the distance until we get to that point. So in this particular case, if we use a large value for b, we're going to cut the distance by that factor. So this is a multiplicative scale factor in the horizontal direction, but in this particular case, we're doing a horizontal compression. I'm letting the words do the work here. So if our horizontal compression factor is 2, then it's going to compress the function by a factor of 2. So all of our distances end up getting halved. If our horizontal compression factor is 1/3, then we're going to compress this 1/3 as much as we were just holding on to it. So it gets relaxed. And all of these values then, the distances to their original x values, to their points, get tripled. All right, and then C kind of does the same thing. If you add 1 to a particular number, right? We're starting here. We add 1 to it. Then we find its function value and then move it back. So our whole function is moved this way. If you add 1, everything gets shifted back left by 1. If you pick this value and you subtract 1, then you're looking back 1, taking this function value and then pulling it back over here. So this is a horizontal shift. But the weird thing here is that it's in the opposite direction as our vertical shift. And let me check on Edzu here. Yep, there it is. Circulation of a fluid with velocities. U sub theta of r. Good times. I may not be the person to do this one exactly. No, you're fine. Okay, it's a circle. So that's good. When you say does not include the origin, is the origin completely outside of said circle? I think I'll be able to... might be able to get something. We'll see. Okay, so our vertical shift is going to be the same direction as the sine. Our horizontal shift is going to be the opposite direction as the sine. This is sometimes known as phase shift. However, really, phase shift is b times c. So if you were to distribute the b into both the x and the c terms, this would tell you the amount of shift compared to the period, which is really distracting, and I don't like using it. So most of the time I just go with, okay, look, this is the horizontal shift, it's C. So if it says x minus 1, your horizontal shift is 1. That's it. The reason that I do that is that, again, we're just talking about a distance. Just talk about the distance. If you talk about phase shift, that's specifically talking about compared with the period And again, it gets hard to discuss it. Meh. Our horizontal compression factor also tells us what the frequency is. So how many more times are you going to go through the same motions as the original function in the same amount of space? So if it's 2, then you're doing 2 periods within the space of one usual period, one typical period. If it's 1/5, then you're doing 1/5 of a period within the usual space of one period. So it gets pretty cool when you start talking about this stuff and start, you can't see what I'm doing, talking about this stuff and saying like, okay, let's do like, I could put in an A, B, C, and D almost immediately. And you should, in theory, be able to come up with the values that you need for it like very quickly. Because if you do it the way that I did it, what you're going to say is, okay, where is my, and in my pre-calc classes, we start from the very beginning of class doing this. Where's my origin point? Right? The place where it's usually 0, 0, where's that been moved to? You just have to find the 2 shifts. How much has it been moved over and up? Done. There's where the origin point is. This one, slightly harder. It's not actually on the function, but it's here. Right? How far has that point been moved over and up? It's your shift in both directions. Right? Move that. Then you say, where's my initial point going to be? Well, that's this one. So the initial point for this kind of function is going to be starting from wherever your shifted origin point is, it's the amplitude beyond that. If it's positive, it's up there. If it's negative, it's down there. Ta-da! Like it's not particularly difficult. And then you say, oh, now we just go 1 period away and mark it again. And then go halfway. We know that that one's on the opposite location. Halfway again, it's at the zeros. Halfway again, it's at these quarter points. I can do an example in a bit, but just for a second, let me try and answer Edzu's here. So nope, circle. Well, even if it's not. Oh. Thank you for keeping me hydrated. Okay, so let's just assume that this is any sort of closed figure. It doesn't have to be a circle at first. We're saying that it does not contain the origin, so the origin point is here. And DC, or DS, is going to be any segment that is going to look at like what is the overall, you said it in here, what is the circulation of this fluid within this segment? And then we're going to sum this up over the whole thing, which is the same as taking the integral. Okay, so it's either, so gamma is going to be equal to the integral around some particular surface or curve. I don't want to use surface. Around some curve, Now it does happen to be a circle in the other case, but we'll do it in general first.